Assalamu alaikum warahmatullahi wabarakatuh. Today we are presenting our project algorithm analysis entitled empirical performance analysis of sorting algorithms, merge, quick, insertion, selection, and bubble sorts. Here is our group members: Sheikh Ahnaf, Adil, Abdunur Abdul Qadir, Ali, Rami, Bassam, Muhammad, Abu Salam. Sorting is a fundamental concept in computer science and is essential for data processing, organizing, and retrieval. Many systems such as databases, operating systems, and data analytics applications rely heavily on efficient sorting to improve performance. From a theoretical perspective, merge sort, quick sort have a time complexity of O n log n, making them efficient for large datasets, while insertion sort, selection sort, and bubble sort have a time complexity of O n square and are generally inefficient for large inputs. However, theory alone does not always represent real-world performance. In real-world application, algorithm performance is influenced by several practical factors such as input order, memory usage, implementation details, and hardware limitation. Because of this, some algorithms that are theoretically slower may actually perform better on a small or nearly sorted datasets. Therefore, the main goal of this study is to empirically evaluate execution time and memory usage, support information algorithm selection using statistical analysis. The objectives of this project are: first, to conduct an empirical performance analysis of 5 sorting algorithms: merge sort, quick sort, insertion sort, selection sort, and bubble sort. Second, to evaluate their efficiency based on execution time and memory usage. Third, the experiments are conducted using array sizes from 1,000 to 100,000 elements, 3 data conditions: random, sorted, and reserved sorted. Multiple representations to ensure reliable results. Finally, an over statistical analysis is applied to determine whether performance differences are statistically significant and provide practical insights for algorithm selection.
Assalamu alaikum. My name is Sheikh Ahnaf Adil, and I will be starting my part of the presentation with methodology overview. To begin with, the algorithms we have tested are merge sort, quick sort, insertion sort, selection sort, and bubble sort, as Abdinur has mentioned before me. And the performance metrics of our research are execution time of each run of every algorithm in milliseconds and the memory usage in kilobytes. And the tools that we have used during our research are C++ to measure the timing of every run of every algorithm, Python script to track the memory usage, and to record the results we used a Microsoft Excel sheet, and lastly RStudio to perform analysis of variance, or ANOVA for short. The process of our research for every run of every algorithm was to create a dataset and then run the dataset through the algorithm, then measure and record time and memory usage and record the results in a Microsoft Excel sheet, and lastly perform ANOVA on RStudio based on the results in the Excel sheet. That was the entire process of our research. Now, for dataset and experimental setup, we have used only one computer throughout our project, which is Rami Bassam's computer. The hardware specifications of his laptop are as follows. The processor is a 9th generation Intel Core i7. The RAM size is 32 gigabytes. The storage type is an SSD, and the operating system is a Windows 10 64-bit operating system. the dataset setup for each algorithm. The dataset sizes range from 1000 to 100,000. The input conditions were randomly sorted data, and reverse sorted data. Each test was repeated 10 times and an average was calculated for the purposes of analysis of variance or ANOVA, which we performed in RStudio. And we used the same hardware and software throughout our project. Each algorithm ran and recorded the results in an MS Excel sheet 10 times for each dataset size and input condition combination. For example, a test run could be of merge sort algorithm, and the dataset to be run through merge sort would be a randomly sorted data of size 100,000. This could be an example of one test run. In total, each algorithm ran 210 times, and all 5 algorithms ran a total of 1050 times in our project. Now, for performance comparisons, we will start with discussing execution time results. From our findings for randomized data, we found out that quicksort is the fastest across all input sizes, followed by merge sort, insertion sort, selection sort, and lastly bubble sort. We also found out that merge sort is the most stable choice for randomized data, and that algorithms with a time complexity of O of n squared scale very poorly and have taken the most amount of time. Now, continuing our discussion for execution time results and performance comparisons, we will be now discussing average execution time under sorted data and reverse sorted data. When data is already sorted, bubble sort turns out to be the fastest algorithm, while selection sort appears to take the longest amount of time. The primary reason for this is, although the data set is already sorted, selection sort still makes comparisons among all the elements in the data set, which results in selection sort taking the longest amount of time. Now, for average execution time under reverse sorted data, when data is reverse sorted, merge sort turns out to be the fastest algorithm, while bubble sort is the slowest, as is expected.
Assalamu alaikum warahmatullahi wabarakatuh. My name is Rami Salam, and today I will be presenting my 3 parts, which is usage, memory result, ANOVA results, and conclusion. So let's be starting with memory usage. For this first slide, we are looking at the memory usage of all sorting algorithms when the data is completely random. The main observation here is the merge sort consistently use the most memory, especially as the input size becomes larger. This makes sense because merge sort needs extra space to create temporary arrays during the merge step. For the rest of the algorithms, bubble sort, insertion sort, quick sort, bubble sort, insertion, quick sort, and selection, the memory usage is quite similar. These algorithms all operate mostly in place, so they don't require a lot of additional space. Overall, what we can conclude from random input is that memory usage doesn't change as time performance, and also time complexity plays a much bigger role in algorithm choice than memory impact for most of these cases. On this slide, we are looking at the memory usage results for all sorting algorithms under 2 conditions, which is sorted data and reverse sorted data. Starting with the sorted data set on the left, we can see the merge sort and quick sort consistently show the highest memory usage across all input sizes. This is expected because merge sort required additional space for merging, and quick sort uses stack space due to recursion. On the other hand, algorithms like insertion sort, selection sort, and bubble sort use much less memory because they are in place algorithms with minimal overhead. Now, on the right side, when the data is reverse sorted, we notice a similar pattern. Merge sort and quick sort still require the most memory. So, overall, input sizes, input order does affect memory usage slightly, but the ranking of algorithms is still the same. Now let's move to the next part, which is ANOVA results. This slide shows the ANOVA statistical test we use to analyze the performance differences between the algorithms. One way ANOVA helps us check whether the differences in execution time are real or just a random variation. Our hypotheses were H0, all algorithms have the same execution time, and H1, at least one algorithm's execution time is different. So the results show an F value of around 104 with a B value of 3.29 times 10 square minus 22, which is way below the 0.05. And this means the difference is statistically significant, so we reject the null hypothesis. In simple terms, this tells us that the algorithms do not perform the same. Their execution times are different, and algorithms you choose is really matters. And by the way, quick sorts it considers as faster than the other algorithms. Finally, to conclude our project, I will be given an overall review for all algorithms. So first, quicksort is the best performing algorithm. It gives fast execution times and handles large datasets. Merge sort is also a strong option, especially because it's stable and has expected performance. Insertion sort works best when the data is already sorted or almost sorted. However, selection sort and bubble sort are not ideal for large datasets because their execution time increases too quickly. But the most important thing is that there is no one perfect algorithm for every situation. The best choice depends on the dataset side, whether the input is sorted, reverse sorted, or random, and the specific performance requirements of the stack. Thank you so much.